Alright, welcome back. So we're going to finish up some sorting stuff, then talk about algorithms, and we'll see how much time we have for Unix and Linux fun. So we just finished talking about merge sort, and now let me prove to you that you can't do better than n log n for what's known as a comparison sort. So a comparison sort is all the ones we've talked about so far. There are ways to do it without comparisons, but we'll get to that. So a comparison sort is a sorting algorithm that uses comparisons to do the sorting. So less than, greater than, less than or equal to, whatever. That is a comparison. So you have to use these comparisons to figure out which order things are in. And the idea is, I'm going to show you that there's a lower bound. N log n is a lower bound on the number of comparisons you need to make, because making one comparison is constant time, and if you have to make n log n of them, then you're guaranteed to do at least n log n time for your algorithm. Okay? So you can't do any better with comparisons. So let me show you that. Let me show you all the permutations that you could make with 1, 2, and 3. Let's say that you knew the array that you were given had 1, 2, and 3 in it. You don't know what order yet because you haven't compared them yet, but you know that it holds 1, 2, and 3. This is the worst case. You need to figure out, using comparisons, which one of these permutations the array is in. It could be 1, 2, 3, it could be 1, 3, 2, it could be 2, 1, 3, it could be 2, 3, 1, it could be 3, 1, 2, it could be 3, 2, 1. Okay, it's one of these 6 permutations. And you have to use comparisons to figure out which one it is so that you can then sort it, okay? Because knowing which permutation it is enough to sort it, because then you know the order of everything. So let me show you that making a comparison, like taking a look at the first 2 indices and being like, oh, hey, was index 0 less than index 1? Question mark. If that's true, then you know that you're in one of these cases. You have one of these arrays. Okay? Not this one. Not this one, not this one, not this one. That just cut off half your space. And if you cut off enough space, you'll be left with just one array that's left, and you can sort it because you know the order. Okay, so less than at best, any comparison, at best it cuts the possibilities of which array you're in, which permutation you're in half. So another way, said the other way around, x comparisons, it cuts off 2 to the x possibilities. Okay, so we made one, we'll have to make another to cut off hopefully half of that, maybe just 1, 3, and we're golden. Okay, we found which one we're in. So if we solve this equation, 2x equals n factorial, we will know how many permutations we need to make to sort the array. How many comparisons to make. That's x. To sort the array. So let me prove to you this. Let me move all this. Whee! So we need to solve this equation. And I'm going to show you a lower bound on the number of comparisons. So 2 to the x equals n factorial. Okay, let's take log so we can solve for x. X equals log base 2 of n factorial. And this might seem like a dead end, but n factorial is n times n minus 1 times n minus 2 all the way to 1. And this is lower bounded by, well, just take n over 2 to the n over 2 power. So it's like, here's n over 2, multiply it by itself n over 2 times. So it's like take this side and make it even smaller. So it's definitely a lower bound. I hope that makes sense. It's totally a lower bound. And we can do this then. This is going to be greater than log base 2 of n over 2 to the n over 2 power. And then you can bring the n over 2 out, right? And eventually you can get rid of all these constants. And it'll be, oh shoot, something along the lines of with enough work, log base 2 with an n at the front, so n log n. Okay, that's my hand-wavy argument, and I'm saying that this is smaller than x, so you have to make more comparisons than n log n. Okay, there's my proof. Hopefully that makes sense. I can be more rigorous in office hours if you'd like. So that's the idea. And so you can't do better than log n for a comparison sort. Well, what can you do? You can get it down to O of n. In the worst case, for integers. And here's one algorithm that does it. It's called radix sort. And what it does is it takes advantage of the way that integers work. You know that the biggest unsigned integer, and a signed integer is even smaller, in terms of digits, it has at most 10. Okay, that's the biggest one you could have. 10 digits. That's a constant number. Ooh, baby. Okay, so what we can do with that is, let's say we had these numbers, 1, 2, 3, or let's get these out of order, sorry. 489, 713, and 147. So those are my three numbers. I need to sort them. Here's how you do it in linear time. Well, you make a bunch of buckets. A bucket to keep track of each digit. So we're going to sort per digit, if that makes sense. Stare at this long enough, watch the algorithm example little animations in the book. This is so fancy. So first we're going to sort by the least significant digit and just keep on going because we know we have at most 10 digits. So we're just going to do it. We can do a loop 10 times, go through every number 10 times. We'll have sorted every possible integer, okay? So we can loop through all the digits n times. So loop through each of the 10 digits and loop through each number. As like the outer loop and then the inner loop. I guess I had it the right way. So just loop through each of the 10 digits and then the inner loop loops through each number to put it in the proper bucket. And this ends up being O of n time because if we have these numbers, we're going to first sort by the least significant digit, and then we'll have shifted these to 3 comes first, right? So we'll then have made 713 in that order because we're going to sort by the least significant digit. 713, then 147, then 489. So now these are in order, that digit. And then we'll sort by these digits, and they just so happen to be already in order, so they're not going to change. And then we'll sort by these digits, and that's actually going to be sorted order. 147, 489, and 713. So you only need to sort 3 times and look through all n of them 3 times because there were 3 digits. Okay? So you just sort by each thing in order, and that will give you the sorted order of everything. And if you have a constant number of digits that you're working with, and usually you do because you have bounded numbers, you've just made a linear time algorithm to sort. Isn't that cute? So that's fun. So that's radix sort, and that is the end of our sorting saga. Okay, now it's time to talk a little bit about algorithms, and then I'm going to show you some cool terminal tricks that there's just no better place to put it in this class than this lecture. So let's get started with algorithms. So let's remember what an algorithm is, just briefly. It's a sequence of instructions that solves a problem, performs a computation, it does something for you. And we know very well now that not all the algorithms are created equally. We've made faster ones, slower ones, ones that take a lot of space. Okay, so we have possibilities. We can prove that some problems are quite hard, and you'll learn more about those in upper division. And others have like a trick that makes them really fast, and I'll show you one of those. And others still we have absolutely no clue about. Like, is there a faster algorithm? We're not sure. Maybe we're just not smart enough and we haven't found it yet. And if you've heard of P equals NP, that's what I'm talking about. That's the best example there. So let me show you a trick that makes some algorithms very fast. And it's called greedy. A greedy algorithm. So a greedy algorithm, it's one that makes what's known as a locally optimal choice. So it's like, I'm going to have candy for dessert. I'm going to have candy for breakfast. That's what I want right now. And it ends up being the optimal outcome. Like, I don't know, maybe your eggs went bad and you would have died had you eaten them. So it worked out well for you to have eaten the candy, even though that was a horribly only locally optimal choice. Okay? That's the idea. So make the locally optimal choice, the one that looks good to you right now from your tiny point of view, and it ends up being leading to the correct outcome. The final answer is correct. So here's an algorithm example. Make change with the fewest number of coins. And let's pretend we had like British coin system. So we have 20 pence, 10 pence, 5 pence, and then 1 penny. You can do the same thing. This algorithm still works with 25 cents instead, but it's easier for me to explain it with 20, 10, 5, and 1 coins. Okay, so making the change with the fewest possible number of coins. And the greedy algorithm is, well, okay, man, you needed 55 cents. I'm just going to give you 2 20s, and then a 10, and then a 5. Let's make it 56, why not? And then a 1. I'm going to start with the largest coin denomination, and then until I can't go anymore, I'm going to keep giving you those, and then I'm going to use the next largest. And that is optimal for most coin systems that exist in the world. So the idea here is, okay, this is optimal. It's the least number of coins because you would have had to have duplicated some. You would have had to do something silly otherwise. So this is kind of the hand-wavy proof. Okay, pretend that you gave me something other than this. I'm going to prove to you that my number 5 coins was still optimal. So you must have, if you didn't give me this amount of coins, you must have made this another way. And the only other way would have been for you to have duplicated something. Okay? Duplicated something too many times. So like here, you gave me 2 10s instead of a 20. And it is the case for these particular coins, and the ones that exist in the US as well, that if you gave me any other number of coins and you pretended it was optimal, that would have not been the case, or you would have given me exactly what I gave you. Because you can always find 2 to combine into a 20, okay? 2 to combine into a 10 or 5, things like that, or 5 to combine into a 5. That's the idea. You would have always been better off having done my greedy algorithm. Okay, so that's the proof that it's going to work for this set of coins. It's not always the case that it works. Here is one example. So let's pretend you only had 1 cent, 3 cent, and 4 cent coins. Okay, so these are the ones that you have, 3 and 4. And you were trying to make change for 6 cents. Well, you'd be forced to do 4, 1, 1. Does that make sense? You'd start with the 4 and like, okay, I can't give you any more 4s, so let's try 3s. Oh, I can't give you any more 3s, let's try 1s. Then you'd notice that that is not optimal. So you can do 3, 3. So it doesn't always work, but sometimes it does, and oh man, it's fast. It was linear time. It was constant time, essentially, because you only had a constant number of coins. So that's greedy. That's fun. I'm going to show you an example of that. And now, a fun thing that you will also learn in an algorithms class is called dynamic programming. And we've seen it a little bit already. You just didn't know what it was called. It's kind of like divide and conquer, but it's slightly different. So dynamic programming, it's a class of algorithms solved using smaller versions of themselves, so just like recursion. But you need some special cases to say that this is a dynamic programming problem. It's just a fancy term. It doesn't really mean a whole lot. You have to have optimal substructure, so the solution needs to be built up by solving the same problem on smaller inputs, which is usually the case for recursion anyway. You're going to build it back up. And there also has to be this thing called overlapping subproblems, and this is what differentiates this between divide and conquer. Okay? So the naive recursive algorithm, it would keep getting called in the same input, and we've seen this already. So we need to somehow get rid of this overlap. So this is the key idea. You get rid of the overlap. You save it. Save the results of those smaller recursive calls so that they're not recomputed. Okay, that's the key. And I'm going to show you 2 examples, one of greedy and one of dynamic programming, and they are on this fancy website called LeetCode, if you've heard of that. It's an algorithms like competition website. So let's go there. Whee! So here are my notes. I was looking this up. So let me make this larger. Here is a problem. Given a string s and a string t, check if s is a subsequence of t. And so for example, here's ABC. Check if ABC exists somewhere in AHBGDC. So there's the A, there's the B, there's the C, they're there. How would you find them? And how would you do this greedily? Because that's the answer is you can do this greedily. So here is my greedy idea. Because the non-greedy way is like, okay, I gotta search for find the A's, find where all the B's are, like try and like permute all this, put it in here, see what's there. It's difficult, but a greedy algorithm works. Just laser focus yourself on the first character. Try to look for that in the T. Then, once you found it, start looking after there in the rest of the string for the next character. Then once you found it, start looking in the string, starting there, for the next character. And that's a greedy algorithm. You're only considering the next character. Okay? Only consider next char in order. Okay? So you're just going to make sure that, all right, if I'm looking for ABC in A, X, C, B, R, C, Z, I'm going to, let's say I found the A, like I'm going to start looking for the B everywhere over here. Okay? Because I just have to find one B, and then I can just like get rid of all these other characters and make ABC out of it. And then once I find the B, I'll just look over here for the C, and hopefully I'll find one, because if I do, then I can just get rid of the other ones. And so then I finally find the C, and I've solved this problem. Okay? So here's my code for that. It's you start at the right end of the string, and you always look for the next character. Something got cut off, sorry. As far left as possible. Oh, I'm so sorry. Don't know what I was saying here. You start at the left end of the string, always look for the next character as far left as possible. Okay, so it's possible that the string that you were looking for had size 0, in which case it's always, a 0-length string is always in some other string. Otherwise, you're trying to look for a non-empty string in an empty string. It's never going to be there. Otherwise, then you keep on searching. So find the index of the character you're searching for starts at 0, like I'm looking for the A first, and then I'm just going to do this while loop, on and on and on. Okay, so just keep on looking for that character I'm looking for. If I find it, then I'll start looking for the next character. So hopefully that makes sense. And the idea is it's greedy because you only have to worry about which next character you're looking for. Okay, you just go from left to right, find the first one, and then you know that you can maneuver this string by deleting some things to just make it ABC again, if you find everything in order. Okay? So that is the first example. That's greedy. Let me now show you dynamic programming, and it actually has to do with calculating the nth Fibonacci number. So it doesn't look like it, though. Here's the problem. You're climbing a staircase. It takes n steps to reach to the top, and each time you can either climb 1 or 2 steps. How many distinct ways can you climb to the top? So let me show you this. So here's your little staircase. So here's you at the bottom. Then here's the staircase. First stair, second stair, third stair. Well, you know, like here are your feet. You can go up 1 stair at a time, or you like take those giant steps and go up 2 stairs at a time, right? So there's 1 way to get to the first stair. There's 2 ways to get to the second stair, because you can go straight there, or you can go up by 2. You see that? And then to get to the third stair, the idea is, well, you could either take this route and go up by 1, so you have 2 possibilities there, or you could have taken this route and have gone up by 2, and you had 1 possibility to get there. Okay, so it's always ways n minus 2 plus ways n minus 1 to get to the next place. Okay, so the slow way of doing this is to just code just this. And that's actually Fibonacci if you look at it long enough. So isn't that cute? So let me do this the very slow way, and then we'll do some dynamic programming. I'll show you how you do that. Oops. So Vim stairs, not CPP. So the idea here is we want to know how many ways we can go up the stairs to get to a certain step. So int ways, int n steps. And we've just proven that in the recursive case, it's ways n minus 2 plus ways n minus 1. That's how many ways we could have come to that stair. And then we need a base case. There's one way to get to the 0th stair, and one way to get to the first stair. That's the idea. Those will be our base cases. If n is less than 2, return 1. Otherwise, we'll return the summation. And this is just Fibonacci. You see that? And we've talked about why this sucks. Oops. There's a lot of repetition, so I can't do like ways 200. It'll never end. Way too much repetition here. See, this will just take until the heat death of the universe now. So we don't want that. We want a better way. So we're going to memoize things. Is the way we say it. I said the word memoize, not memorize, which is weird. Don't worry, you'll see that again in an algorithms class. Let's do the fast ways. And then we can do the ways of 200 if we wanted to. So the idea is, sure, we know how many ways to make n things, but we're going to keep on calling it with the same numbers. So remember that you keep on calling things with the same numbers. Because, for example, you're going to call ways of 4, which is going to call ways of 2, which is going to call ways of 3, which is going to call ways of 1, which is going to call ways of 0, which is going to call ways of... sorry, this is 3. It's going to call ways of 2, which is going to call ways of 1. It's going to call ways of 1, which is going to call ways of 0. And we've duplicated so much stuff. Those are the base cases, so it's not too bad for them. But the bigger cases, they do get duplicated. And especially if this was like ways of 5. Then you have ways of 4, and you have ways of 3 over here. So this entire subtree got copied. We're just redoing everything. This is horrible. Life sucks, and we can fix this. So let's save. Let's save intermediate results. Because the first time we've saved, W2 will stop right there. We won't go any farther down the tree. And then the first time that we save ways of 3, we'll stop right there the next time we see it. We won't go any farther down the tree. And so in each case, we'll only ever be calling it once to get the final answer for the first time. Then each other time we can give back the saved value. So, only call it once for each n now. And that's linear time. That's much better than the original naive way, which is to the n time. Okay? We don't like that. And we can fix it. We can make it linear. If we just save results, we can say like unordered map between ints and ints. So this is constant time unordered map because it's a hash table. Let's call it M. And we could be like, all right, in the base case you can do that. Otherwise, if M has a value for N, just return it. Otherwise, calculate the value and save it so that we never have to recompute it. And this is what I mean by overlapping subproblems. I should probably say that as well. Okay, so we'll just save it. Be like, okay, well, solution equals this. Then m dot in place, n solution, return solution. Bam, we've done it. So now it's going to save the result. It's going to calculate it once and save it, and we're off to the races. I need to make the proper recursive call. This is just, oh wait, sorry. This one up here, I called it ways slow. And it goes so far that it overflows, but it does it in linear time. It's super fast. Okay, so that is dynamic programming for you. And yeah, again, this is something I'm not really going to test you on a whole lot. If anything, it'll be a multiple choice question on the final. But it's good to have seen this at least once before you are like forced to do all this stuff yourself. Okay, now finally we get to have a bit of fun, and we're gonna do cool stuff with the terminal, and I'm just gonna teach you some cool programs that you might have not seen before. I'm gonna make sure you know about them. So here are 4 that I don't know if they go together, but I thought that they belonged together for some reason once upon a time, so that's why they're here. So the first thing I want to show you is echo. It just takes any number of command line arguments and then it just prints them right back out. So you can be like, okay, echo hi, and it's like hi. Hi, hi mom, hi mom. You can give it a string, like, doesn't really matter. Dun dun dun. Just like that. But when you have strings like this, sometimes there are special characters and that's no fun. So that's what echo does. You can just give it a bunch of stuff and it'll just print it right back out. Semicolons are special. That's another thing that you need to watch out for. So only give it words. Okay. That's echo. Not too bad. It's a simple simple thing that you can totally write yourself. Cat, short for concatenate. It like outputs a file to you. So, for example, I have stairs.cpp in my current directory. I can say cat stairs.cpp, and it's going to print it out. It's just going to output it to standard output, to like cout. Okay. So you can also write this one, super easy. Now man, if you've never heard of this one before, this is very important to know. So man, cmd, shows you the manual page for this command. And oh man, is that going to save your life. So you're like, okay, what? Echo is very simple. man echo. What does it do really? And then you can use your up arrows and type Q once you're done. You want to stop reading the manual. So you can use it like Vim as well. Oh, echo takes some options. Don't output the trailing new line. Backslash escapes. Ooh. Shows you its history. Oh man. Echo can do some interesting things sometimes. What about cat? Ooh, it takes some options and then you can give it multiple files. Ooh, wait a second. Cat stairs.cpp stairs.cpp. And suddenly I have it twice. See? That's fun. So I can make as many files as I want, come one right after another using cat. And you can do a bunch of different things. Suppress repeated empty output lines. That might be useful one day. But the manual, oh man, it's beautiful. And oh man, our fearless leader, Richard Stallman, helped write this one. What? That's amazing. It's a piece of history. Cat. All right, so then time. What do you think that does? It just shows you, wait, no, that's not the current time. What's it doing? Time times how long a program takes to run. That's really cool. So you say time command, and it'll tell you how long it took to run. So man time, run programs and summarize system resource usage. That's useful. You know, I made you do that for your binary search stuff, linear search stuff. You could have just used time. So I say time dot slash stairs. It didn't take a whole lot of time, but maybe if I make it do like ways of 25 and make it slow. Curses. Nope, I didn't change it all the way, sorry. I must have undone something in a weird way. I thought I changed that. Hey, okay, this one ends, and it took 1.64 seconds. Beautiful. That's time. Now let's have fun. So Linux, it comes from a long line of Unix things. So if Unix came before Linux, it was an operating system invented by some very smart people at a telephone company of all places. The motto for Unix is that everything is a file. And so you can give like the output of one program as the input of another, because you can just get the file that is the output. Okay, you can pretend that it's a file. So that's what piping is, and I think I'm gonna show you that after these other ones. So command less than file, it gives the contents of file as the input to the command. Okay, so that's weird, I know. I can say echo. Do I want to use echo here? No, I can say cat. No, either way, this is not as easy as I thought it would be. What's a good one that I could use here? Yeah, so let me just show you what cat does if you don't give it anything. It'll start reading a file from standard input. And once you end it, it'll stop. So I typed things and it just typed them right back to me. So cat technically can take a file as input because it can take the standard input as input. It can use cin if it wanted to, if it wasn't given a file. And say cat give it stairs.cpp. And so it took it as input in a different way. Okay, it took it as standard input. It's as if it typed it in. Okay, that's the idea there. The other, more interesting one is the other way, and it's the opposite. Save the result of CMD in the file, into file. Save the output, which is fun. You'd be like, okay, echo hi mom, output that to out.txt. Bam. So it didn't show me the output because it redirected it. And so now if I cat out.txt, I get to read the file back. Beautiful. Okay, that's that. You can append to a file if you want to using 2 greater than signs. And now piping is so interesting. Sends, so piping involves this pipe character. It's shift and then the thing above the enter symbol, the enter key. This is what it looks like. If you say command 1, pipe command 2, and you can do this as many times as you want, command 3, etc. This first runs command 1, gets its output, sends its output as input to command 2, gets command 2's output, and sends that as the input to command 3, and so on and so forth. This is very, very, very powerful, and the way that I want to show it to you is using less. Okay? So less, all it does is the opposite of more. That's super helpful. These people are funny. So what it does is it just shows you a file and you can scroll through it if there's extra stuff. So technically it's kind of running less when it's showing you these man pages. So I can say man, or I can say less and then a file name. Stairs.cpp, and now I can like use the up arrow and down arrow. So this is what I'm giving it. I'm using this using pipes and less to show you your grades. And you can say Q to get out of it, but you can scroll up and down as much as you want. View the whole file. So that's what less does, and less also takes input. You can say less with nothing. Well, it needs a file. It knows when it's been given a file. You can say the following though. Cat stairs.cpp. Normally, that's going to output it to the standard output. We can pipe it to less, and less will get it as the input. And suddenly, the output of cat, which is the contents of the file, is given to less. And oh man, can we look at it in less now? Which is extra special if you can do something like echo hi mom to less. Yay, and now I'm looking at hi mom. Quit. So that's super nice to inspect the output of a program because the output might change sometimes. Okay? grep. It's a pattern matching program, so it's going to find something in something else. So look for a pattern in a file. You can look through the input as well. If you use a dash, there's a bunch of different options, but I'm going to show you the simplest one. You can learn regular expressions if you want, but here's the idea. searches for a string and a file. So I can say man grep. Yeah. So I'll say grep ways in stairs.cpp. And it's going to tell me all the different places where it finds it. And this might not be helpful. This is really helpful if you're debugging, actually. It highlights them in different colors, which is nice, but we can go further. We can find line numbers as well. Where is that? Dun, dun, dun. N. If we use grep n, -n at the beginning, that's one of the options. We can use -n. Say grep -n. It'll tell us also the line number on which it finds those matches, and that is super helpful if you're ever debugging. Okay, a few more. These are all so fun. The next one is diff. It shows you the difference between two files. So you give it two files, a.txt, b.txt. It'll show you the difference between them in a weird way, but you'll get used to it. So you just give it a bunch of files, usually two. There's a bunch of different options, and the output is interesting. So I'm going to make two files now. So, hello world, blah. That's the first file. And b.txt is going to be the same, but I don't know. This can be hello mom, the world with a space, and blah can be the same. Yeah. So I can say diff a.txt and b.txt, if you remember what they are. And what it's going to do is it's going to tell me where things were different. It'll be like, okay, lines 1 and 2 in the first one, and lines 1 and 2 in the second one were different. On the left file, which was the a.txt, was the first thing that you gave. The left file had hello and world. The right file had hello mom and the world with a space. See that? So that is the output of diff, and oh man, is that useful. Once I finally have time to update the autograder, that is what I will be adding for the next batch of students next semester. So that's what diff does. rm just removes a file. Removes a single file. Potentially you can remove an entire directory as well. You use -r to remove a directory, and it's done recursively. What do you know? So -r removes an entire folder and all its contents. So that's remove, and then move is the last one on this page. It moves a file. So it renames name 1 to name 2. It moves it to somewhere else. So potentially you could have said like rename foo.txt to bar.txt. Sorry, it's move. Foo.txt to bar.txt. That will rename it. Alternatively, you can also move it somewhere else, like move foo.txt to some other folder slash. If you just give the slash, it'll keep it named foo.txt. If you want to give it another value as well as move it to another folder, you'd say you'll say bar.txt. You give it the new name, okay? It knows whether or not the last thing you give it was a folder or a name. So that's moving things on the terminal. And with that, we just have a few slides left, and this is where I want to stop because we're out of time now. So that is the entirety of the lectures for this week. I'm now going to go and get ready to do a review session. So I'm going to record that eventually, and you'll have that in time for your midterm. So be sure to watch that as well, and hopefully you'll be using some of these cool commands and the ones that I'm going to show you next week as well as you use the terminal. So I'll see you then.